So dear students, in the last video you could understand what is dielectric polarization. Very simple to say, dielectric polarization is a staging or reorientation of dipole moments in the direction of electric field. That is, some net dipole moment is developed in the developed per unit volume. Any element of volume, there will be several number of molecular dipoles, okay, and the net result is called polarization. Now, what is the effect of polarization on the dielectric? That we will discuss now in detail, and then we will extend its application to the parallel plate capacitors. Okay, let us see. Okay, result of polarization. You see, this is electric field, right? This is a dielectric sample placed in the electric field. What happens when the dielectric is placed? The molecules take a form like this. They are aligned like this: negative, positive, then negative, positive, then negative, positive, then negative, positive. Now see, just on the surface, what is the collective effect? Let us conclude like this. In this volume, you see, leaving a layer of negative charge here and leaving a layer of positive charge. That is, and another inside this becomes neutral. Everything becomes nucleus. So this deposition of negative charges on the surface, let the surface density is minus sigma p and it is plus sigma p. So we can conclude this is the net result of polarization. A layer of negative charge, that is surface density. Surface density of charge will be developed on one side negative and other side positive. Now if we apply directly to a parallel plate capacitor, see what happens. This is the plate of capacitor, this is another plate of capacitor, negative plate, positive plate. So positive plate contains positive sigma, and this is due to polarization, this is negative sigma. So what is the result? What is the net surface density of charge? That is sigma minus sigma p. But in case of conductor, if it would be conductor, what happens? Sigma p would be equal to sigma here, and net would be equal to 0. But in case of insulator, that does not happen like this, but a negative charges will be installed here, and that will reduce the electric field by how much? E naught minus EP. Okay, and one thing what we can say, that sigma minus sigma p will depend on what is the original sigma, and this is what sigma minus sigma p will be equal to sigma by some constant k. Here k is called dielectric constant. Okay, continuing this, what we can write? Electric field. Now what is the net electric field? Net electric field will be equal to E naught minus EP. Very simple, sigma minus sigma p by epsilon naught, and thus that comes to E equal to sigma by k epsilon naught. This is the result of polarization. Now let us now immediately apply this process or this idea into our parallel plate capacitors. Capacity of a parallel plate capacitor with a dielectric completely filled between the plates. Okay, let us consider a parallel plate capacitor with negative charge position, and a dielectric is completely filled between the plates. Okay, its dielectric constant is K. Okay, now see the net surface density of charge. Let us write this sigma minus sigma p. Okay, surface density of charge equal to this much, and this is equal to sigma by k. Clear? So electric field between the plates now will be equal to what? Sigma by k epsilon naught, that is equal to sigma by k epsilon naught. Okay, this is a equation number, magnitude of electric field. Now let us write this equation number 1. Now if you want to find the potential difference between the plates A and B, then this V will be equal to what? E into D. Correct? The previous relation we have already used this. So V will be equal to what? Sigma into D by K epsilon naught. This comes to q d a into k epsilon naught. Okay, and that will give from there what you can write directly. Just write here only, that c equal to what you know, q by v will get here k into a epsilon naught by d c, and a epsilon naught by d is the capacity with the capacitance with no medium between the plates. Okay, so here c equal to k times c naught. Okay, then what is the effect of the dielectric medium between the plates? Very simple. We have got the electric field becomes 1 by k times equal to sigma epsilon naught by k instead of sigma epsilon naught. Okay, so electric field becomes 1 by k times. Number 2, immediately V, that is potential, equal to E into D, nothing more. So it will become 1 by k times. And what happened to capacitance? Capacitance will increase, that is the new capacitance becomes k times of the voltage. Now from this solution only we can define dielectric constant k also. K over here will be equal to C by C naught. Okay, that is the ratio of these two capacitance. One, the first field with dielectric, and with respect to where it is there is no medium between the plates. So what happens? What is the net result? The insertion of a dielectric medium between the plates of a parallel plate capacitor. What happens? That will increase the electric field. Let me see what is the physical situation takes place. Suppose this is a dielectric. This is a parallel plate capacitors with air. Now, if we use this dielectric medium between the plates, its capacity will increase by k times. K is the dielectric constant of this medium. Okay, if we use another medium, the dielectric constant will change and the capacitance will change. Okay, thank you.